All right, so thank you to the Philly Dynamo user group for inviting me to speak. I want to just apologize to the community about last week. I spent about 6 hours or so at the Logan airport, had a canceled flight and all kinds of craziness. So I was really bummed. I was looking forward to meeting a bunch of people and seeing some other Dynamo users in another city. So big shout out to Peter and Effrey for giving me a second shot at this, even though it's virtual. Hopefully this presentation is exciting. I am speaking tonight on what I'm calling Bimpasse. Dynamo is means for design actualization within Revit. A little background about myself. I am originally from Portland, Oregon on the West Coast, but I've been in Boston for about a decade now. I went to Colorado for undergrad and then came to Boston for my master's for graduate school at the Boston Architectural College. I currently work as a digital design manager at Gensler in Boston, and I've previously worked did a stint in construction and then various architecture firms in the Boston area before that. And if you haven't heard of me before, I'm extremely passionate about the design technology community. I'm always trying to find ways to both get involved and share my ideas and kind of spread as much knowledge as I can, because I think that through my work experiences, the best way to kind of evolve as an industry and broaden my skill set and the skill set of others is through sharing. So some of the ways that I do this in Boston is I'm a co-founder of the Dynamo group in Boston called Dynamo-litia. I also, we recently started a design technology interest group called Encode Boston. I am co-planner for the BeyondAEC Symposium and Hackathon, which you'll see a little bit about later. And I also led an event last fall called the Design Technology Throwdown at a local industry event in Boston called Architecture Boston Exposition. You've probably all heard of Gensler before, but the Boston office helps represent the Northeast region, along with New York, Morristown, and Toronto. And all the things that I do as digital design manager, I couldn't do without this all-star cast behind me. So we have 5 axes at Gensler that consist of Revit, computational design, creative media, performance, and making. And so these individuals are always kind of exploring what technologies we use and how we can kind of venture into the future of the practice using these different things. And one of the most common questions I get in all the things I do at Dynamo is this: so how do I get this into Revit? People are always asking, like, if you're familiar with Grasshopper, you can make all of this parametric logic and visual programming, and then you just hit a button called bake, and it turns into geometry in Rhino. But unfortunately, Revit doesn't exactly work that way. While you can use nodes and use parametric logic, it doesn't just enter into Revit the same way that Grasshopper and Rhino work. You have to use a means that Revit understands and kind of speak its language. So a little disclaimer about the presentation tonight. I'm calling it Bimpasse because there's that tipping point, kind of that impasse that happens with BIM and Revit, where we want to make stuff in Revit. We want to quickly kind of create things or modify things, but there is a little bit of a learning curve that needs to happen in order to do so. And so my presentation tonight does not include all of the ways to do things in Revit, but it does include a lot of them that I've kind of cobbled together over years and that I've personally used myself on projects. And then also I'm going to try to explain it in using the easiest terms possible. I use a lot of the simplest nodes like strings and numbers and things that are kind of out of the box, because I wanted to make it so that people that are maybe newer to Dynamo can easily pick up and understand what I'm putting together. Apologies if some of those, some things you're about to see are a little longer than they should be, I guess. So starting with annotation stuff, if you're creating various geometry in Dynamo, like we see in the upper right corner, there are ways to then turn those into both model and detail curves. So the node names are model curve by curve, and detail curve by curve. And what it's essentially doing is taking the Dynamo information and it's converting it to Revit elements through the Revit API. Some things that you have to consider is that the polycurves need to be exploded or broken into their different subsegments. And then NURBS curves, when they come in, they're not lines like you see in if you just draw a random model or detail curve in Revit, but it's actually a spline element, which you can also draw in Revit. Another thing is filled regions. Sometimes we want to drop like a hatch or kind of mark something up with a filled region, even though they're not the most intelligent elements in Revit. You can take Revit curves like a poly curve and then in the perimeter lines of that and then establish a filled region in Revit. One thing to note is these are view specific, so you have to either define, like you see, hover around here, you should be able to see. So you have to either define the view that you're, up here, that you're trying to put it in. So I've done some kind of filter by Boolean mask and matching to get this level 2 floor plan. Otherwise, it won't be able to be placed because that's a view specific item. It does not work with NURBS curves. That's one more point to note, is that you have to do the same kind of workflow or another workflow we're going to see in a minute about converting it to a poly curve so that Revit can understand it. Another thing that you can do is place 3D components or families into Revit in any place. So I just took a simple example here and a point array and placed a bunch of trees. This one's really simple. I took a handful of nodes, obviously, but this could be helpful for placing, furniture items and all kinds of different things. Another one is hosted elements like doors and windows, even face-based or surface-based, ceiling, floor-based stuff as well can work. So what you have to essentially do is define a point that you want to place it on. In the workflow that you see here, I actually selected a Revit element. So I'd created a wall on the Revit side and then pulled that into Dynamo. Up in the left corner of this workflow, one thing to notice is one of my favorite ways of getting information from Revit is there's a select model element button, which I'm hovering over. That will pull in the actual element itself, and that's evidenced by the Revit element ID that pops up with it. However, if you share this file with somebody else or you open it at a later time or in a different model, it may not have that specific element ID, and it sure as heck won't match that same wall or whatever item you're querying from the model. So I use our Arcolab select by element ID node, which allows me to kind of bake in a element number. And in future things, if I switch models, let's say, I can select a new item or a new wall and feed in a different element ID number, and then it will select that every time. So that's a little more robust than the out-of-the-box select model element node. And then what I'm doing here essentially is I'm using some logic in this upper shot to get the geometry of that wall and then explode it into its surface, divide the ISO lines for each one. So what's the center line of those surfaces? Get the point, take the center point of each line so that I can get the lowest Z value, which means that I'm going to ultimately filter out the center line of this wall at the very bottom. So a little bit of logic that happens there on the geometry side in order to isolate a center line, which then coming down is a little too long to fit in the screen, so we're coming down to the second one here. I was able to take that and then I just chose 2 different points. So I have a point at parameter on that line at 1/4 of the way in, 20.25, 25% of the way along that line, and 0.75, 3/4. And then I can place, in this case, a window in the upper group of nodes here and a door in the lower group of nodes. So you see them placed here. The one thing is the window will come in at the ground level because the way this family was built is you have to define the sill height itself. So that's one thing to consider when you're using hosted elements, is that you want to make sure to identify what parameters come with those items, and then potentially add a last step, in this case for the window, with the element.setParameterByName node, where you can then define the 2 feet, in this case for me, of the sill height, and this window moves up in space as it should be. The same goes for if you want to change the width, or the width and height of the window, or the width of the door, or the family type even after something's placed. You can drop generic stuff in and then swap it. All of that boils down to an element set parameter by name node. You can also place 2D detail components. In my experience, I've done a ton of this stuff, but it is possible if you're adding detail things, or if you have a 2D family that you want to, whether it's some sort of annotation or arrows or something like that, that you kind of want to move around a plan, you can absolutely instantiate 2D detail components with Dynamo at whatever point that you subscribe. Going back to the previous workflow, same goes for this one. If you are to first query something from the Revit model and use that as the basis for why you're generating points, obviously then those 2D elements will go in to the right location and they'll match up with your plan or with whatever view you're working with. Also, you should consider which view you want this to go in. So I brought all the views in Dynamo, filtered again to match the second floor plan, and then fed that in. So these 2D place families will only live in that view. On the Dynamo side, you can do some pretty neat things with color as far as an analysis goes. This is a geometry from a workshop, Dynamo workshop I taught at Dynamo-litia a couple years ago now. And it's essentially just analyzing the vector direction of coming off of the perpendicular vector direction coming off the face of these panels on this wall. But this, using display by element geometry color, it only shows in Dynamo. So that's only helpful for what you're doing on the Dynamo side. It doesn't actually get it to Revit. So how can we get color in Revit? Using element override color in view, we can kind of do a hack, and we can override the color in the specific view we're looking at. So in this case, I placed a bunch of generic family boxes in an array, and then colored them in that fashion. One thing to note is I have a little bit of logic going on here with, I took the total count of items, and then using the remap range, I kind of had to adjust for minimum and maximum color values and feed that into the color range node, which creates a spectrum, kind of a rainbow color, and then applies that over let's see, we have 16 families here. So you can see that gradient shift over the course of all those shapes. Obviously, override color in view is a little bit of a hack at times. Like if you go into Revit, into plan, and right-click on any item, you can override it there. But it is a little bit tricky because it's not an ironclad way to alter something's characteristics or its visibility settings. And it makes it tough for like a team member or yourself to figure out how that item got colored later. So that being said, there's another way to do it with materials. So you can use the same element set parameter by name that we've seen with driving, say, dimensions of a certain family or object. But in this case, what we're going to do is actually query an existing material from the Revit model. So we're going to use material by name and just feed a string up here into, we're going to feed that name into material by name, and it will create an actual Revit element that recognizes a preset material that I've created here on the Revit side. So in this case, I just named one red, put in the appearance values and all that, and then was able to drive that as a material parameter into the model and overwrite these families. One thing to note is that I tried doing this on a type parameter, material type parameter, and it was not happy. So it's important to make it an instance parameter so that it affects one family at a time, and then you just need to go through and so make sure you have all the families selected on the Dynamo side in order to color all of them the same, Or you can start to do something similar to the last workflow. If you have all these colors would need to be pre-loaded into your Revit project in order to then match them up and drive them through Dynamo and the set parameter by name. So then looking at something like walls, pretty simple. The way walls are created in Revit is very similar to the way that you manually create them in the software. You click on a point and then drag a line and define what your wall is and set an offset height, and then that's what generates the element. In this case, there's a tool called wall by curve and height. And if you have a dynamo curve that you've created, so here we have 2 points and a simple line between the two, you can use wall by curve and height node to set what the total height of that is, what your start level is, and the type of wall that you want, and it will generate that. There's also another node called wall by curve and levels, and the only difference with this one, instead of an unconstrained height, you can define 2 level inputs, and it will constrain that wall between, say, level 1 and level 2. Using the set parameter by name, it is helpful if you decide you want to change offsets of something. If you have a real specific, like a parapet wall at the top of a building or something, you can then make sure that it's constrained between 2 levels and then start to adjust the heights of the offsets for that upper and bottom portion. You can also do arced walls. So what's nice is, you can create this on the Revit side, but it's interesting to be able to make curvilinear walls driven from Dynamo. So up here, we just have a simple arc by 3 points, and then it's feeding in the unconstrained height version of the wall by curve and height. You can also use polycurves. So just using some geometric logic here up in the example window, I was able to create a polycurve. It's kind of a Z. The key here is that you must explode the polycurve first. So these walls want to be created by individual line segments, not a series of joined line segments, which is what a polycurve is. So one step in between, I had to explode them, and then you could still give them the same wall by curve and height, unconstrained, define height, whatever, to get your whatever shape you want, and they will join. And then also, I took a shot at a NURBS curve wall. So I did not think this would work, and sure enough, it did not. However, there are ways to get a representation that's pretty close. And so you cannot create a spline on the Revit side, or a wall from a spline on the Revit side either. So that's just not going to happen, but you can with these smaller segments. So what I do is I use something, one of my favorite nodes is curve or surface point at parameter, in this case curve. What it allows you to do is feed in a sequence, in this case between the very start parameter, which is 0, and the very end, which is 1. You can feed in, define a number of segments along that line that you want to break it into. So here I have 10 segments if you count them off on screen, and it creates a new polycurve by connecting dot to dot to dot all the way to the end. And then I can explode that freshly created polycurve and use that to create my wall. Obviously, visually, this isn't the smoothest thing. So there's a balance that can be struck between breaking this thing into more segments to make it look more curvilinear, I guess, except for, some people might still have an issue with, if you have a handful of segments, it looks too rigid like this. If you have too many segments, it still may or may not look great. But also, like, if you get a million wall slivers, it gets a little difficult to manage because you're adding more geometry to Revit, and it's things that could potentially get moved or deleted or something like that. So keeping those elements together is important. Another option you have is to do wall by face. So this one's a little tricky because it depends on a Revit mask. So that's how the tool works in Revit itself, is you create a building massing, some sort of shape, and import that massing family into your Revit project. Then you are able to select the face of that object, and it will adapt for curves to try to kind of do a curvilinear example like you see here. It will accommodate for a lot of different geometries. It will also allow you to update face if you alter the family and then re-import it. In this case, what I was able to do was just create a twisting massing family, put it in Revit, and then select that and use some Dynamo logic to apply the wall to the faces and define the center line. In this case, you can do exterior, interior, whatever you want, but that's one input it's looking for. One last note on that is one of my favorite ways to create kind of generic objects in Revit is using the spring nodes springs by dot family instance by geometry. And what this allows you to do essentially, rather than an import instance or an SET or some of the cruder ways of getting an element into Revit from Dynamo and other means, this allows you to actually use the Revit family templates that kind of come out of the box for generic models, special equipment, all kinds of different things. So although I did not test this in preparation for this presentation, it's possible to create a mass family from your Dynamo geometry using the Revit massing family template, and it will automatically import that and load it into your Revit model. And then if that works, you can select and query that newly created item that was driven from Dynamo and run it through this workflow in order to apply walls. Also could potentially work for floors, roofs, things, all those kind of different elements. So then I ventured into kind of floor territory. So similar to walls, floors are pretty simple. You get an outline curve and then just feed that into floor by outline type and level, defining what type of floor you want and the level it lives on. To take it a step further, you can kind of pull in different individual curves. So say I chose a rectangle in this shape, but say you have a kind of wacky customized shape of some sort that you've been piecing together using Dynamo geometry logic. As a test, what I did was I joined the four sides of a rectangle, and then I shuffled their order to see if it would still be able to recognize and create that item. And sure enough, with the individual curves in a shuffled order, it was still able to generate the floor. So it's not important that they're in sequential order. Probably a good idea as a practice because Dynamo often wants geometry to be in a nice kind of circular or ordered format in order to make its geometry. But if you're working on something that's getting a little out of control, but it still defines an enclosed shape, then you should be fine. Same goes for polygons. So I created this Z shape, whatever it is, with polygons, and then I was able to take that poly curve and feed it into floor by outline type and level, define the family type that it is, and then tell it what level it'd be on, and it made that shape. I went a step farther to give a shot at doing a floor by NURBS curves, and I found out in the process that it's not possible to create using the native spline tool in Revit is not possible to create floors. And the reason for that being, if you can see in the demonstration file here, over on the spline tool, the pink lines on the right, Revit spline does not allow you to actually reconnect itself to the end. There's no snapping function in order to close that shape out. So no matter how many times you click and try to match it up or move it around, it just won't connect. It can be a little frustrating. So the workaround for that is actually leave it a little bit open, and you can draw a straight line segment to enclose that piece. And that will allow you to actually generate a floor in Revit, and that will work. So a little bit about that background. I mean, I kind of just figured that out by messing around, but a little bit of background on why the Revit tools won't allow you to create a Revit floor from the spline is covered in Paul Winter's parametric monkey blog that I found online. I thought it was absolutely fascinating. some of the limitations of that tool. So what I did in the Dynamo side was say, create a fully enclosed NURBS curve that I'm going to feed into a 4-element, but in this case, just trim the end of this thing back a little bit so that I can enclose it with, by connecting a straight curve segment and actually make this all one enclosed shape. It's just not a true NURBS element. And once I did that, I was able to feed that into Dynamo, and sure enough, it worked. And all you get is just one little blemish on whatever corner. So maybe you strategically try to hide that thing, but 2 little lines over the overall shape of that is pretty not noticeable. So then the next step, trying to take a crack at ceilings. This is something that I have tried many times in the past for different projects and things I've worked on. So the limitations in the Revit API are that you cannot actually create ceiling elements. There's some information that I grabbed from the internet here, where on the left you get this, there's a table of the types of elements you can create and what their kind of API calls are. On the right, there's some posts about, or this is actually from the Revit Ideas site, which allows you to post different ideas for Revit improvements. And so it's just clearly stating that this isn't a feature that's currently available. And I've included the link in this presentation slide deck so that you can actually go there, visit it, and potentially upvote it to get it higher with the Revit team. With that being said, I have come up with a workaround, actually 2 workarounds that allow you to circumvent that limitation. So in this case, the first one that I did was I just created the same poly curve that we were using earlier, and in this case I want to generate as the ceiling instead of a floor. So using the clockwork selection set by elements, you can actually import these model curves, or excuse me, these lines, these curves in Dynamo as model curves in the Revit model. The problem being that if you're on a project floor plan that's got a lot of stuff going on, a lot of annotation, you don't necessarily want to be importing curves into space and then losing them potentially. Or if it's a really complicated ceiling, there could be a lot of lines that are going every which way and adding model size. So the selection set tool, if you're unfamiliar, is something that I think is rarely used. And what it allows you to do is select a bunch of things in your view and save them to what's called a selection set. It's basically storing the elements IDs of those items in Revit so that you can go back to the menu under, I believe it's Manage tab, or yeah, I think it's under Manage, and open up the selection set menu and reload those elements again. So this clockwork node is extremely handy to actually wrap those, immediately after those model curves are instantiated in Revit, wrap them up into a selection set that can be recalled. And then the last step is to actually go in to create a fresh ceiling by sketch and just pasting the lines in place. Sometimes it doesn't allow you, or maybe all the time it doesn't allow you to paste those lines exactly in place. So you might have a little bit of a visual cue or something that you can paste them and create your ceiling and then move it around to align it where it needs to go. Another approach is you could just create a floor, just like the workflow we saw earlier, and using the lines, if you go and edit that once it's created in Dynamo, or excuse me, on the Revit side, and then edit the sketch, steal the lines, you can also paste those into a freshly created ceiling element by sketch. You see a little bit down here of the lines, the curves come in as model curves. You select those sketch elements, and then boom, the ceiling is created by sketch. Placing rooms is also something you can do in Dynamo. So it's dependent on room bounding objects, otherwise it will just go in unplaced and kind of run off to anywhere. So if you do not have wall elements and things that are actually defining and bounding the room, you could create room separators by curve, another fantastic clockwork node that allows you to just generate a shape of some sort based on Dynamo curves, and then that goes into the model. And the last step is that room by location is a node for placing a room at whatever level that you want, the plane defines kind of a plane origin, or origin point defines the location, and then you just give it a name and a number value. Another workflow that is pretty handy is creating curtain walls. So this workflow is the same as just the basic wall creation task, where you're defining an underlying curve and the height of something, and you're creating a wall type, which happens to be a curtain wall. Where it gets tricky is that oftentimes we want to define the spacing and some of the information surrounding that actual Revit curtain wall item. So you can do this a couple ways. On the Revit side, if we look below, we see something actually created in Revit. If we if we generate a specific or duplicate or establish a specific Revit curtain wall family that we want to use, that has specifically defined mullion spacing and mullion sizing and panels that are embedded and hosted within it, that's one way to go. Another way is to actually duplicate and create a fresh curtain wall type that does not have any grids in it. It's just simply the frame, and maybe it has one panel placed in it or whatever to kind of populate the center, but it's a blank slate. If we use Dynamo to create a wall by curve and height and define that this new type in there, it will just generate, based on the surface, a new curtain wall. The next step would be then using some geometric logic on the Dynamo side to divide up the ISO lines and create horizontal and vertical intersection lines on that surface that we can then instantiate in Revit as curtain wall grids, which will split it up. And that act of splitting it up actually defines where the mullions are going to live on this thing. So as long as that system is the mullion is defined, it will pop up and it will divide it and mullions will pop up. The last step is you can actually use set parameter by name, and you can see a little bit in the example image here. It's not shown in this image, but you can actually derive the subfamilies, the mullion types for the exterior frame as well as the interiors, and also the panel types. If you want to get into different panel swapping for vision glass versus spandrel or metal panel, maybe infill items, or even getting into different color glasses or different colored treatments, you can get pretty custom in curtain wall land by generating the overall shape with Dynamo and then driving how the grids are splitting inside of that. Another workflow that I've done for creating some wilder shapes is using the structural framing by beam by curve node in Dynamo. So what this is essentially doing is taking a structural framing element, or like a Revit beam, a structural beam family, and then it defines it on a curve inside of Revit. So what I've done here, and you see in the upper top, is just take a simple, it was like originally a CSS generic steel family that I modified to be a solid extrusion. And then I defined what the radius parameter was for the start and end of that item. So it allows me to kind of manually flex things on either end to define a certain overall shape and size. I then use this Dynamo structural framing by beam by curve node to actually populate them in space to match Dynamo geometry. So what you see here is a student from this last semester of teaching at the Boston Architectural College. She had a design that was a custom column, kind of decorative column piece to help support her acoustic ceiling tile layout in her final project. And first we worked on how to create branch logic and then actually apply these families along those curves. And as the last step, use the set parameter by name in order to define what the starts and ends of these things. So you get kind of this growth effect of the trunk of the tree, and then the branches get smaller and smaller as they get to the top. Trying to mimic a little bit of biology here. Adaptive components are a pretty popular means for creating complex facade surfaces in Dynamo. So also just in the Revit environment, they can be pretty handy for making some complex shapes. You are also able to really deconstruct any Dynamo surface or Dynamo object down to its underlying point structure of kind of your choosing, and then use that to drive adaptive components. So you can get a little bit more added control and adaptation to bespoke geometry that you create on the Dynamo side. The key to this is some serious list management. And list management is essentially reordering the way that things occur in lists and sublists throughout Dynamo in order to really define the way that a particular geometry is created, or that the way that data is structured in order to meet a specific end goal. And what you see here in the examples is that I have a adaptive, basic 4-point adaptive component family up here, starting with one corner and working around clockwise to a fourth corner. This top piece of Dynamo is essentially just creating a geometric Dynamo surface, and then or creating some curves and using some math, and so you get a curvilinear surface. That surface is then broken down into points of a determined spacing based on the surface.pointAtParameter node, which I mentioned. I really like this one. It helps you kind of divide and space things out evenly across any surface. You then use some wild list management, as I mentioned, to chop all of this up and restructure it, with the end goal being that you need to make sure that all the points that are organized from surface.pointAtParameter into columns and rows of information, they need to be restructured so that they go in order of 1, 2, 3, 4 clockwise in 4-point clusters. So with this logic, it's essentially flipping the list rotating every other level, excuse me, not rotating, but reversing every other level, so that you can then chop them down into 2s and combine them into 4s, and then rotate the order of that list in order to go from 1 to 4 component points in the same order as the adaptive component. And what we get here is when we use this adaptive component by points node in Dynamo and define what panel we want to use, it actually populates along that surface the adaptive component. And if I click on one, you can just kind of see the points there applied. If I did not have it in that order, it would not be happy and not work. So it's really critical to get that in the same, to match the same sequence. And then using the same kind of workflow, you can also apply this along trimmed surfaces. So whether a surface is trimmed on the Revit side, whether you have a bespoke surface of any shape that may not be orthogonal, which this kind of point-at-parameter approach in Dynamo likes orthogonal shapes, so it can evenly divide them up as much as possible. In this case, we have a kind of a corner bitten out of this curvilinear surface, and so it was really important to establish a logic and accurate counts for what conditions are along this curve. So sometimes you get, if we're starting with automatically with squares and 4 points, sometimes you end up with 3 instead, and there are places where you end up with 5 as well. So in this case, you would need to modify an adaptive component to account for 3 items, a triangle, and then 5 items, a sort of 5-sided polygon. And then once you have that, you can divide these into separate lists. Remember that logic is important, what corner you're starting with and how you're moving around the edges of that adaptive, and then drive that into Revit and populate your surface. So all of these things that I've showed today are ultimately striving for a better Revit experience. Like the question stated in the beginning, is how do I make this Revit? How do I get these things to show up? Or I've spent all this time making this kind of computational design. How can I start to populate Revit elements that would inform my project? And I think that Dynamo is the key to be able to connect between these platforms and automate or optimize some of the workflows for creation. One thing to consider with interoperability whether that is generating something from Dynamo geometry, or it's feeding something in from third-party platforms like Rhino, SketchUp, CAD, all these other softwares that we use in our daily workflows, is the important thing to realize is that generating elements in Revit is just like learning a new language. So you can't just say, you know, I speak English and I'm just going to kind of talk louder at you to get you to understand me and do what I want. In this case, it's like the difference between Spanish and Chinese, let's say. It's very different language and set structures and characters. And so Dynamo is that kind of connector between those two worlds and the translator between those languages. But we have to have a base understanding of both of those platforms and those languages in order to be able to define what we're trying to say. So that's why some of the workflows we've seen here are helpful for understanding the way that you create those classic elements in Revit that we do on a daily basis. I created this diagram to try to help explain a little bit of the questions I get from between Rhino and Revit and why things don't just turn into geometry on the Revit side. So on the left, what you have is, let's take a basic Rhino surface. So if we're creating a curtain wall, for example, on Rhino, and it's going to be used for design intent and, you know, perspectives and presentations and even some high-end rendering. The key in order to work with Revit is that we have to have really clean layer management. So the key things that we're trying to organize here are making sure that the surfaces are all accounted for. If we're looking at an entire building mass design, making sure that those surfaces are included as their own layer, and then potentially the base curves, because those are something that we need in Revit to define where the start of those different walls are. The boundary curves and the entire shape itself could be helpful. And then what are grid lines that are defining the curtain wall that will eventually define the curtain wall on the Revit side. And lastly, just the overall massing itself. Is it, if you have a funky building shape, or even if it's just an extruded rectangle, what is the shape that it's going to be in the end? And just understanding a little bit more about Revit is we have surfaces that we understand as, you know, maybe glass elements or walls or something as geometry on the design side. And we have grid lines, which are essentially splitting up those sub-elements, but it's possible that there's a representational geometry of sorts that's in the form of a sweep or of an extrusion that's representing mullions for the purposes of rendering and visual understanding of that design. On the Revit side, it's a little bit different. As we've covered earlier, walls are driven from a base curve, which has kind of a defined start and end point, and an overall height that can be constrained by bottom and top levels and offsets on top of that, or it can just be an unconstrained height of a specified dimension. In addition, that surface is split up into grid lines that then describe the emollient, they cause the mullion placement to happen. And then both the panels themselves and the mullions are in their own right elements that are hosted in this overall curtain wall piece. So there's a lot more going on the Revit side, but we have the ability to kind of steal and translate information from Rhino over to the Revit side of things and then define the same things and establish the same design. This diagram is something that I created to try to better describe the interoperability workflow for a design project between Rhino and Revit. So these are probably some of the most popular tools, Rhino on the design side for kind of driving shape and form and visualization and diagramming. Revit on the production side for starting to establish some of the hardline items like building grids and actual elements and wall thicknesses and details and all that stuff, and annotated floor plans and printing. So it's oftentimes really desirable to establish some sort of workflow between these two programs. And that can be done with a combination of Dynamo and Grasshopper with intermediary of Excel. So a good start, or just a general workflow, could be if you have basic grid and structural grid information, whether it's a new building or an existing, you can start to establish Revit grids on the Revit side, as well as level heights and some of that information. Once you have that created, you can get that information out using Dynamo and feed that into a basic Excel file that describes the start point and end points of geometry. It describes the XYZ location of those points and the kind of width and spacing of the grid elements, as well as level heights themselves. That information can then be fed through Grasshopper into Rhino, and on the Rhino side, now you have lines that are describing where grid lines are, where you can have level lines be established from the offset heights, all that stuff. So now you have two different types of geometric entities that are interrelated and are sharing the same coordinates, because your original geometric elements came from the Revit side. So they will land in somewhere in Rhino that you can begin the basis of modeling. On the Rhino side, you begin making shapes and starting to organize your layers and doing the actual geometric and kind of shape-driven design process. And then you can build tools that reverse this interoperability workflow through Grasshopper, Excel, and Dynamo to then instantiate as Revit elements in a very similar process to some of the things that we've looked at tonight. Once those things are elements, you have pretty much converted that underlying Rhino design intent into Revit elements for documentation. Obviously, you would want to do some review and validation on the Revit side to make sure things came in properly. It's possible that meetings with the client, or delivering these elements in some sort of drawing set would result in feedback, and then the cycle continues where you pass information back through to establish Rhino geometry, and then there's the final process of maybe if there's a design push, rewriting some of those Revit elements over and over and over until you ultimately arrive at a final design. One caveat to this process is on the Dynamo side, you have custom packages like Rhino by Nate Miller's Proving Ground, as well as Mantis Shrift by Arcolab and Conrad Sabone, that allow you to actually convert Rhino geometry without this interoperability need for Grasshopper. What Grasshopper does get you is the ability to convert data back into Rhino, but those also can somewhat be generated using those two custom packages for Dynamo. So one more point I wanted to touch on was this concept of data serialization, which is a key component of this interoperability workflow we just covered. Data serialization is the process of actually converting geometric elements into their purest form, into just numbers that describe their overall coordinates. So we could break a panelized surface, let's say, into the actual corner points that are driving those panels, and those coordinate points have an XYZ coordinate in Cartesian space. So if we can capture that into a list of XYZ coordinates in a formalized structure of data, that structure then can be reverse engineered in other software formats. In this case, if we're feeding things in through text file, CSV, JSON, all these different data formats, through Dynamo, deconstructing it and then reverse engineering it into Dynamo geometry, we now have the basis for being able to convert all kinds of geometry formats into Revit elements themselves. So last thing I just wanted to share was give a shout out to an event that we're hosting in Boston next month. So on Friday, July 20th and Saturday, July 21st, we will be hosting a hackathon and symposium at this newly unveiled incubator space at Sasaki here in Boston, and they're actually in the Watertown area. And on Friday, we're going to have a symposium for 4 hours featuring 3 guest special speakers. And then the hackathon will start on Friday evening and roll all the way into Saturday afternoon. So if you are someone that's trying to kind of get your feet wet in the design technology community, or trying to meet more passionate people like yourself, or perhaps you're someone that's constantly, flirting with development and creating new tools and trying to find better interoperability workflows across software platforms, I highly recommend checking out our event. Registration should be going live any day or sometime next week, so keep an eye out for that. The website for that is BeyondAEC.tech if you're interested in finding out more. And lastly, I was just going to open it up to questions, but since we're doing a virtual call this time, we'll just hold the questions for later, and maybe people can reach out to me individually. You can find me on Twitter at KCMArchitect, and I do have a blog, martinportfolio.com/blog. Posts are getting a little stale at this point, but I do keep an eye on it and can respond if you have any questions or want to comment on a certain post of the past. So that's pretty much it for my presentation today. Again, apologies for the Philadelphia Dynamo User Group crew. I would have loved to meet you guys, but hopefully there will be another opportunity to catch up with you in the future. So thanks again for organizing this, and take care. Enjoy the summer break, everyone. Bye.